on equilibrium. It's pretty much going to have an example of almost every type of problem you can see on the test or on the AP exam. And I want to be able to go over it as much as I can, but I'm not going to be able to do every single problem all the way through. I don't have time. I mean, it would be, seriously, it would take me at least the whole period. I need time to give you the first half of the test. So let's look at something that will be as easy as this. When you're given amounts, you're given moles, and you're told the size of the container, and then you're given the equation. You don't have any ICE problem to do. You're not solving for X. You're just going to plug these in and solve for KC. And KC, as you I'm sure know, is just going to be products raised to their coefficients over the reactants. Now, I want to point out to you, as I do these, I won't be able to do all of them all the way through, but I can at least point out to you the mistakes you'd be making. All right, first off, I'll write down I must show the work. That's a big mistake. If you don't show me this formula, and you just start throwing numbers around, I don't know if you knew what to do. So I can't give you partial credit. So this is what I would need to see. I need to see products raised to their coefficients over reactants raised to their coefficients. I need to see the numbers plugged in. Now let's start talking about the mistakes you would make. Starting with forgetting to divide by the 5-liter container. Did you all remember to do that? Okay, don't forget. Whatever size container they give you, make sure you divide by that. If you forget that, yeah, it's going to be 2 points off, but I'll still give you partial credit. That's why you show the work. So, second mistake, just reading left to right. I get people all the time. In the review, first period, that's exactly what happened. They put that number over that number and over that number next. Now, that's how they're written, but that's not where they go. NH3 is the product. His concentration was 0.565 divided by 5. What is that? Anybody have that? What is that? Anybody? 0.113 squared over N2's, which was 3.01. What was that divided by 5? 0.602 raised to the first power times 2.1 divided by 5? 0.420 raised to the third power. That's what I would need to get full credit on this, showing me all that work, and then what is your asking about to be for that? Point what? 286? All right, that's what KC will be. Now, of course, that's as easy. It's almost as easy as it gets. Yeah, it's got coefficients. Yeah, it's got a size of a container, and there are times that I don't even put that in there. But seriously, I didn't have to do an ICE problem. I didn't have to use a quadratic equation. It was pretty easy. All right. Also, I noticed in this, and a lot of the problems I've been giving you, I've been lazy in not putting down that there are gases next to them. Okay? Let me just make that point. Because on the test, I'm not lazy about that. I put all the correct solutions in there, or correct phases in there. If these weren't gases, I would have a problem. Okay? I'd have a problem because if it's not a gas, I can't divide by the size of the container. If it's a liquid or a solid, they aren't even included in the K problem. So I'm not going to trick you on the test. They will be gases, or they could be aqueous. We're going to talk about that next chapter more. But they cannot be solids or liquids. All right. If they aren't included in the equilibrium. And as you'll see with the Le Chatelier's principle questions, check that out. You got to be careful of that when you're looking for that. I bet you a lot of you missed that in number, I think 5 or 6 down at the bottom. All right. So that's a nice easy one. Let's do another one. Okay. The next one gets a little bit harder. This is very much like the problem we saw in the lab when we did the lab on KSCM. We added the KSCM to the iron nitrate. We got iron thiocyanate, and that turned red. So here's how, if you remember, we had an ICE problem with that. ICE. It was, Fe plus SCN equals FeSCN. And, I was given the initial concentrations of these guys. 2.4 moles of A divided by 5 is what? What was A? Point what? 2.4 divided by 5? 0.48, you said? 0.480 for that guy, 0.480 for that guy, 0 and 0 for these, right? You're told you added that much to the container, and at equilibrium, you know you've got 0.300 moles of C. But in between there, what happens? This guy decreases by some amount X, that guy increases by some amount 2X, this guy increases by some amount X. Okay, so 0.480 minus X, 0.480 minus X, 2X, and X. Of course, I need some other piece of information. Sometimes the other piece of information is going to be, like I've given you here, the concentration of C. I'm told I have 0.3 moles of C, which again I have to divide by the size of the container. What is 0.3 divided by 5? Anybody? Somebody did it.
Yeah, that's what it is.
0.6? 0.06, I mean?
Yeah.
So 2x equals 0.0600. Is that right? So x must be 0.0300. Got it? More. These are, I mean, I'm going fast because it's review day. I've taught this. I've done pretty much the same examples multiple times throughout this chapter. I'm not spending my time being careful about every little thing here. All right, you should know how to do this. So you find x, and now you simply plug that back in here, 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 and here, right? And then solve for Kc. When you subtract 0.03 from this guy, you'll get a number. From that guy, you'll get a number. 2 times that guy, you'll get a number. And you'll get that. You plug them all in. Products raised to the coefficients over reactants. I mean, I don't have time to do all of it, but real quickly, C and D would be, what would I be putting in for C? Yeah, be careful, don't put in the 0.03. You have to multiply it by 2, that's what it is, so it'll be 0.0600 squared. D would be 0.0300. Over A and B are going to be 0.480 minus 0.03 in both cases. And then you just get your calculator out, multiply them, and you're done. All right? All right, again, I don't care what the answer is. You have that much work shown with these numbers finished. If you make a mistake with your calculator, oh, I forgot to square that. Oh, I divided it, but I forgot to put parentheses around it, you know. That's going to be 1 point off for stupid things like that. If you show me the ice, you do this, you do that, and you do that, 1 lousy point for the math. So keep that in mind. That's why you show me the work. Yeah.
Okay, for I got a different answer for when you're solving for the C.
For C, well, I got to take 0.3 divided by 5. Do it right now on the calculator.
Okay.
You forgot. Remember, these are the things I'm trying to warn you about. You will forget. You'll forget to divide by 5. You'll forget to multiply by 2. You'll forget to square it down here. These are the little things that if you did your homework, that's why all that homework's over there. So you can practice that and not make those mistakes again. All right, let's get to the next one. Now, that one still wasn't too hard. Okay, if you remember, that's the one we did the lab on, and that wasn't that bad. Now, this one gets to the point where you've got to actually got a lot of algebra. You've got FOIL, you've got the quadratic formula, and all this stuff. But it's done the same basic way. It starts out the same way anyway. Ice. Okay? My initial change in equilibrium. My initial concentration of A, 0.2 divided by 2 is going to be what? 0.100, 0.0500, and 0, right? Your changes, again, if I've only got reactants, we're going to talk about Q in a few seconds. When we talk about Q, he tells us which way he's going to go. But if I've only got reactants here, he's only going to go one way. Everybody see why it has to be that? Minus is on the left, plus is on the right. All right, 0.100 minus x. Now notice what we have here. We have a very similar situation that we had a minute ago. We have everything in terms of x, and at this point I need some other piece of information. The other piece of information this time is not what you had last time. Last time you were told at equilibrium I measured how red it was. That's what we did in the lab. And it was this number, and we said that's what x is. Okay, great, we were able to do that. This time you're not given that, but you are given Kc. So if I know Kc is 0.0537, and I can still, set up my equation of A times B. There's my same, equilibrium equation you're going to use every time. If I know Kc is 0.0537 equals C, his concentration is going to be 2x quantity squared over 0.100 minus x, 0.0500 minus x, right? That's what it should look like. Now, at this point, you're going to get, again, I want to say 1 point, but pretty much most of the points for the problem if you get it to that point. But you do have to do FOIL. First, outer, inner, last, get that guy down there. You got to cross multiply. When you square 2x squared, what do you get, by the way? 4x squared, not 2x squared, right? Because you're squaring the whole thing. Eventually, you get it into the form like this, right? And you plug that into your calculator, because I gave to everybody in here. Does anybody not have one of those graphic calculators? Okay, if you don't have one, I have extras tomorrow, so that you can borrow it, and it's got the quadratic formula on there. You plug it in there. You don't have to do a long handle. It'll save us some time. Eventually, you get x. I don't have it worked out. Does anybody have x worked out? What is it? Anybody? If you don't, it's not a big deal.
I had 0.00933.
Okay, assuming that's right. Assuming that's what x is. Again, we're just doing the review today, a very quick review. You would then go back, plug him in here, plug him in here, plug him in here, and that would be your final answer. Your final answer would be the equilibrium concentrations of each of those three guys. Okay? All right. So notice they all they revolve around this equation. Sometimes you're solving for Kc, like I was in the first one, the first two. Sometimes I'm given Kc, like I am here, and I'm solving for x, in which case I plug it back in. Now, I can go further than that. All right? Like, for example, in this next one, I'm going to hint at something else when the volume of the container changes. I'm going to hint at Q. But it starts out with a problem that we've all seen before. Actually, it's easier than what we've seen before because it tells me the molarity, don't even have the size of the container, and asks me to get Kc, and these are at equilibrium already. I don't have to do ice for that part. There's nothing to do ice for. It says they're at equilibrium. So I simply take my Kc. Oops. Where was I? Here? No. That one there? Okay. I simply take my Kc, and I use the numbers as they are because there's no size of the container. I make sure I plug in the right ones. NO2 product over reactant N2O4. All right, so I'm going to find Kc by plugging in NO2's concentration, which is 0.0600 squared, more squared, over 0.770 molar. And I would solve Kc. I'm sure somebody at least has that much done. What do you have for that for Kc?
0.00468.
Okay. So I've got my Kc now. All right. Everybody can get that much of this problem done. Now, that's not worth very many points in this problem, percentage-wise. All right. If this problem's worth 10 or 15 points, that might be worth 3 or 4 or 5 points because it's so easy. The hard part's coming. I'm going to have to do an ice problem because I changed things. Now, let's talk about what I changed. I doubled the size of the container. Now, that means I did this. I took my container that I had my reaction being carried out in, and I pull back on the plunger and I make the size twice as big. Yeah, I've decreased the pressure and I've increased the volume. What effect will that have on my concentrations of everybody? It's going to decrease. Well, no. I mean, overall. Overall, what does it do? It decreases the concentration of everybody, doesn't it? Because it's the same number of molecules in a larger space. Well, it's going to favor the side with more molecules. It always does the opposite. I've made the concentrations too small. Do you all agree it's going to favor the forward, the side with more molecules? I've got 2 versus 1 on that side. And remember, gases pretty much take up the same space regardless. So I know that this guy is going to go that way. It's going to favor the forward. The reason I need to know that is that's going to tell me my minus x's and my plus x's. They're going to be going that way. It's minus x on that side, plus 2x on this side. Now, I know a lot of people, if you look at the example I did maybe from the homework or from the notes, you might say to yourself, there's 2 things you could do wrong here. It sounds like Jared forgot the 2, and I see that. Other people might have put the minuses here and the plus there, thinking, well, when you have a change in the size of the container, in that example, he had the minus on this side. You're not thinking. It's not a question of memorizing what side to put the minus on. It's a question of understanding what I've done. If I change one word on this, if I make this I half the size of the container, then it would be minus 2x and plus x over there. You see? Okay? All right, so, and by the way, I said about Q. I'm going to talk about that in a second. What do I have to do to these concentrations? Why I'm going to have to, since I doubled the size of the container, I'm going to half those concentrations. This guy's going to be 0.0300. And what's half of that guy anyway? 0.3 something? 0.385. All right. Now look at. Say I do this on the test. I don't think I did, but say I did this. How could I make this where you'd have to? I do have a problem. But it's a good time. I should say this now. There is going to be a problem on the test where I'll have you solve for Q. Okay. Now, what does Q really do? Basically, Q is saying, hey, that's what Kc is. What would happen if I had these concentrations? Which way is it going to go? Now, we know because we changed the size of the container, we were able to predict which way it's going to go. But say I didn't say that. Those are just the new concentrations. Does it have to go forward or reverse? You could just plug those in. Remember, Q is just K. It's the exact same equation, just not necessarily at equilibrium, right? So I would plug these guys in, and I would redo it, and I would find that Q is either greater than, equal to, or less than K. If it's less than, it means it's got to get bigger. which is what this guy's going to have to do here. All right, it's going to favor the forward direction. And if it's greater than, it's going to get smaller. Right? Okay. Now, I don't have to do Q here because I already know that because of Le Chatelier's principle. So let's finish this problem. 0.385 minus x, 0.0300 plus 2x. Now, at this point, there's nothing else to do but what we just did a minute ago. You're going to solve the equation. You know what Kc is. Products over reactants. Plugging these guys in. Quadratic form. You're actually going to have to square it first. All that stuff. Quadratic formula. Get your x. Plug the x's back in, and you're all done. All right. So it's the exact same thing we did a minute ago. Only we had to do this first and figure out which way he's going when I change the size of the container. Again, not time to finish all that. You have time to do these tests. You need at least 10 minutes or 15, and we're getting close to that right now. All right. This guy right here. What do I have to do with him? Again, this is just a review. I forgot to write down in here the temperature should have been given as 25 degrees Celsius because you'll need that for the second part. But the first part starts out just like you've seen before. It's a nice problem. Hey, it's a very nice problem. I see. It's a nice problem. Your initial concentration of CO is going to be what? 3 moles of CO in a 2-liter container. What does that mean? 1.50, 1.50, and 0. Minus, plus x. Minus x and x. I know what x is, though. What do I know x is? I'm told the concentration of CoCl2, that's this guy right here, at equilibrium, is 0.0198 molar. Everybody got that? No, I say, well, don't you have to divide that by the size of the container? Why don't I, if you're reading carefully, have to divide by the size of the container this time? Because I told you the concentration was this molar. If I said I had 0.0198 moles, I would have to divide by the size of the container. Okay? So x is this number. Right, x just is 0.0198, which you then plug into here, and you plug it into here. Right? Okay, now when you do that, you can then solve for Kc. Kc is going to be products, CoCl2, over reactants, Co times Cl2. So Kc is going to be 0.0198 over whatever 1.5 minus 0.0198 is. Do you guys have that worked out at all? What is it? So, I mean, the final answer for Kc. Whatever these two guys are. What's your final answer for Kc? Point what? 009404. 00904. Okay. Let's assume that's correct. And again, I don't really care that much. If you set all this up right, that's all that really matters. You're not talking about a lot of points off for your algebra, your math. I say not even algebra, just math. That's your Kc. It wants Kp. What do I need for Kp? What's the equation? What is Kp will equal what? Kc RT to the delta N. Now let's talk about this for a little bit. Okay, I think everybody was here for this. You weren't here for some of you weren't here for the other one, or maybe you weren't. Maybe you were absent on day I did this. What does delta N mean? The change in the number of moles. You're looking at the coefficients up here. So I'm going to take 1, products minus reactants, minus 2. 1 minus, there's 2 on that side.
So that's the equivalent of 1 over.
Yeah, exactly. So that means he's a negative 1, which means you're going to take your RT, and it's going to be the reciprocal of that, to the negative first power. What would happen if they had the same number on both sides? It'd be 0, you just drop him right out of the equation. Kc and Kp are the same. Okay? What are we using for R in this case? 0.0821 liter atmospheres per mole Kelvin. Some of you may have used the 8.314. That would be wrong. By the way, you don't have to memorize any of those. Anyone not get one of these, by the way, yet? This is a sheet with all the equations on it. You're all here one of those days that I gave it. I gave it Friday and yesterday. All right. Well, you're using this one here, guys. The only time we're going to use that crazy one, and I showed you where it came from, where I'm going to get my answer in joules, that's where I'm going to solve for delta G. Because that guy uses joules instead of liter atmospheres. Not a big difference, but there's a difference. All right. So you would plug all this in. I don't know if anybody did this, but did anybody get what Kp is for that? Nobody? Now, whatever. If you plug in Kc, 0.00904, times R times T to the negative, would be basically the reciprocal of that. What'd you get? What'd you get? 3.681? That doesn't seem right. Times 10 to something? There.
It's not. I don't think it's right though.
Oh, okay.
I got the first part wrong.
All right.
So.
Because you remember, to the negative first power means the reciprocal of that. Okay? So you divide, you're actually...
It's the equations you do 0.009, and then
0.0821.
0.0821.
Times-
0.000369.
Yeah, so that's what you got. It's times 10 to the negative third, is it?
oh, I messed up.
You just forgot the times 10 to the negative third. Okay. So that's what KP is. All right, now look at delta G. This is, y'all watching? To do delta G, I have one more thing I have to do here. The equation for delta G was what? Anybody remember it?
Negative RTLS.
Delta G equals negative RT ln K. And we're going to use, since they're all gases, which K do I use? KP, since they're all gases, KP. Okay, if they were aqueous, I would use KC. All right, so delta G equals RT ln K. The temperature has to be given to you. It's 25 degrees, which would be 298 Kelvin. But the R is 8.314 joules per mole Kelvin. That's important. You have to use that one in this case. Okay? And then you solve for your delta G. Now, I don't really care what the answer is, but let me ask you this. Knowing that K, both Ks, are small, smaller than 1, what would I predict delta G to be? Positive or negative? Well, think about it. What is a negative delta G? A negative delta G means what? It's spontaneous. It means it's product favored. Goes this way, right? So what would I expect the delta G in this case to be? Since I have a very small K, less than 1, I'm going to expect it to be reactant favored, not going very far, so it'll probably be a positive number. Delta G will be a positive. Okay? Whatever that answer comes out to be when you plug it in for this. If you want to do that right now, you can double check that. Just making sure you're using the right R, temperature's 298, and then the natural log of K, and see what you get for that.
Do I have to know these equations?
Absolutely, guys. I just asked this. Why I asked if you had the sheet. Because you get to use the sheet on any test. Okay, it has every constant and every equation you need. Did you get a positive value? Did you plug it in?
No, it's natural log.
All right. So, we're almost done with the review, and we need 10 minutes. We only have one team, not even 20 left. So listen. Let's take a look at this guy right here. These are the ones that are on the test I'm about to give you. So let's go over this one time quickly. Okay? I was asking you what happens if I change the pressure, volume, temperature, or add somebody to it. What was the first question I asked you? What was that? Increase the volume. Now, here's what I'm doing when I increase the volume. I've talked about this before. I have a certain number of particles. I pull back on the container. I have the same number of particles in a larger space. So the concentration of these guys decrease. It's going to try to get those back up. It's going to favor the side with more molecules. So you all agree, for 5, for this guy, it's going to favor that direction, more molecules on that side. How about this one? Forward for this guy. How about this one? A lot of people put neither for that in the first class because they didn't see the S there, right? It's going to favor the reverse. Okay? All right. Now, here's the beauty of this. The next one says it's going to decrease the pressure. It's exactly the same answers and logic. All right, what's the next one say? Increasing B?
Yeah, sure.
Now, this is really easy. If I add B, it's going forward.
Yeah.
Right? Yeah. If I add B to this guy, it's going reverse. If I add B to this one, forward. Now, I was disappointed by some of my, in the test, I had to ask about 3 different ways with energy. I think I've asked 4 different ways with energy. Okay? If I increase the temperature, I want you to treat temperature energy just like a reactant or a product. Energy is on the right side. I add more energy on this side. It's going to favor the reverse. It's going to get rid of it. Always does the opposite. That's what Le Chatelier's principle says. Here, I've got a positive delta H. You've got to know. I told you this. You've got to know what endo and positive delta H's mean. This guy positive means he's on this side. Plus energy on that side. If I add energy, I make it hotter. I'm making that side too heavy. It's going to go forward. And finally, exothermic means I have plus energy over here. And it's going to add energy. It's going to go reverse. Okay? Last thing to show you. So, last thing. Yo, take a look at these graphs. Now look at the difference between these two graphs. You watching? Yeah. First of all, I can ask a bunch of questions about this. Even going back to the kinetic stuff. What is this brown one here? It has to be a product because it starts at 0 and it gets bigger. This guy's got to be a reactant. What would you be able to tell by the slope of this line? The slope tells you the what? What's changing all the time like this?
KC?
Polarity.
Wow. Wow. Right. It is concentration over time, which is what?
I don't know.
One word. Begins with an R, ends with 8.
Rate.
The rate, for crying out loud! My God!
Starts at R and ends with
Oh, this is bad.
Yeah.
Alright. Wow, if you don't know that, that's pretty bad. But anyway, why is this a graph of a reaction that goes to completion, and this is a graph of an equilibrium reaction?
0, that one.
Yeah, this guy goes all the way to 0. This guy does not. Where does equilibrium actually establish in this problem? Over here. Is it on equilibrium here? No, where the two rates are equal, right? Okay. What else could I ask you about this guy? Oh, you know what? Here's a good question I could ask you. Is this guy right here going to have a large or a small K? Greater than or less than 1? This guy here. Let me draw another one for you. I could have an equilibrium problem that looks like this.
Large.
What kind of K would that guy have to have? Small, because not much of this stuff actually reacted in the forward direction, right? What does this guy have to be? Pretty large, right? Because you started with 1 molar of the reactant, you end up with only like 0.2 molar of it left. You went mostly to completion. Not all the way, but it is an equilibrium problem. All right, that's it. Now, you need the rest of this time to get these done. Okay, let me